All right, so good evening, everybody. Today I'm going to talk to you about iterative methods. Some of the things that we did study in Maths 407. So, as we said, if you have a matrix AX, if you have a matrix AX is equal to B, where it's A is an n by n matrix, and then B is a vector of n components. So you have an n by n linear system, right? You have some n linear systems, n by n linear systems. Then, in general, we can write these methods, right? We can write these methods. This we can convert this AX is equal to B to a kind of a fixed point iteration method, where this is a fixed point iteration method. So we have x to the power k, x of k is equal to t, xk minus 1 plus ck plus c, where k of course goes from 1 to and so on. So in this case, T here is a fixed matrix. This T here is a fixed matrix, and your C here is a fixed vector. So we write our system, our linear system, in terms of some matrix vector iteration form. And of course, the first method we did speak about was the Jacobi method. So the Jacobi method, if you take your linear system of equation, your n by n linear system of equations, and then you take your A, which is an n by n matrix, and then you write A, you write A in 3 parts, which consist of D. D here means nothing else but the diagonal. Then it consists of an L. L here is nothing but a lower triangular, and then a U, which is also an upper triangular matrix. So these are all matrices: a diagonal matrix, a lower triangular matrix, and an upper triangular matrix. So if you can see here, we have our A here, which is given by A11, A12, on the row up to A1n, and then you can see we have an n by n matrix consisting of A, I, J, I going from 1 to n, and then J as well going from 1 to n. So basically, for this, we can write an A, I, J such that I and J are both going from 1 up to n. Okay. And this gives us an n by n matrix. Then, as I said, we can just compose our A into the diagonal. So you can see here, this is the diagonal, and then the upper, and then the lower triangular matrices. But what is distinction, or the distinguishing thing is your upper and lower triangular matrices, or the upper and lower triangular matrices, we add negatives to them, right? We add negatives to them. So here, the lower triangular matrix consists of all the terms. Here, this is the lower, this is the L, the lower triangular, and then we do have here as well the upper triangle. But in writing this matrix, what we do is that we add negative signs to all the terms, all the terms in the lower triangular matrix, as well as we do the same for all the terms in the upper triangular matrix. And this is basically just because we have decomposed our our matrix A here into an A plus D, an A, which is equal to D minus L minus U. So we add these negative terms to complete, make this matrix decomposition appropriate. Okay. So now, now, once we have that, then what we do is that we now go through the process. So in the Jacobi method, so this is really the Jacobi method. In the Jacobi method, this is the Jacobi method here. So in the Jacobi method, we split now the diagonal from the off diagonal. So you have your D is minus L minus U of X is equal to B. Then you split it into dx is equal to L plus U of X plus B. And if D inverse is not 0, then we can write X is equal to, now we multiply through by the D inverse, is the D inverse of L plus U of X plus D inverse of B. And if we follow the idea of the fixed point iteration or fixed points that we earlier spoke about, then we can see that we have a matrix, an X is equal to Sk is equal to D inverse L plus U, Xk minus 1 plus D inverse of B. And this gives us X to the power K, which is Tj, where Tj is this term here. This term here is the Tj, which is Sk minus 1, and then plus the Cj, which is this term here as well. So now your K goes from 1 up to, let's say, N. And this is exactly how the Jacobi method works. So for instance, if we want to take an example of the Jacobi, then for instance, if we take, let's take example here, right? Let's take an example here. If we take an example as example such as 4, 3, 0, 3, 4 minus 1, 0 minus 1, 4. And then you have some x1, x2, x3 is equal to 24, 30, 24 minus. Then we know that this is exactly our A of x is equal to B. So we can split the A. The A we can split into a D minus L minus U, right? Where now, what is the D, right? So the D is a diagonal, just 4, 4, 4. And every other term is 0. Okay? Then what is the L? What is the L? So L will be all the terms in the lower triangular section. And so we will have 0, then all the terms there, so I'll make them now negative 0, and then this is negative, negative, so I'll have a positive 1, and then I'll have a 0, 0, 0, 0, 0, because all the other terms should go to 0. And then finally, our U, we can write it as, we can write the U is this part here, so we have 0, minus 3, 0, and we have 0, 0, and 1, we have 0, 0, and 0, right? Zero, 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 zero. Okay. So this is your, if you take your X is equal to B, and then you split them into these three parts, then you will be able to have this. You can split them then into these parts, D minus L minus U as this. Okay. Then if you want to solve this, so basically you just have to then follow, multiply through, and then derive your TJ, right? Derive your TJ because you can compute. So the next step is that you take your TJ and you say TJ is D inverse L plus U. Then you derive your TJ and you derive your CJ, which is D inverse of B. Then once you have TJ and CJ, you can then insert them into the fixed point iteration method and then run, giving some xk0, right? So here we are always giving some initial x0, right? Giving sk as initial values, right? So you use this as your initial value, and then now you can run the number of iterations that you want. Okay. The next is that I want to talk about Gauss-Seidel. Okay. So you see that similarly for Gauss-Seidel, what we do is that if we have a linear system, so again here our A is an n by n, then our B is a vector of n components, right? Okay. Then you can again split now your splits. Okay, now you split such that you split the D minus L and U. You split the 2 and minus U, right? You split into these two components, D minus L and then a minus U. So if you do that, then following what you do is that you say D minus L of X, and then the U minus U of X is equal to B. Then you can now take your U X to the other side, to the right-hand side. Then subsequently, you can then multiply through by the inverse of D minus L. So if we do that, then again, we have D minus L inverse of UX plus D minus L inverse of B, right? And then again, this gives you your SK, CG, SK minus 1 plus CJ. And usually you are given, right, you are given some initial value. What is that? You are given an initial value of x0. Okay. So again, if we want to take the same example as we did in the previous case, then we'll see that if we have now, right, 4, 3, 0, 3, 4 minus 1, 0 minus 1, 4, right? Then now, if we want to do the splits, then again, we have DL and U. So again, we have a D, which is going to consist of only the diagonal terms. Don't forget, every other term is 0. Okay. And then you have some L, which is going to be the lower terms. So 0 on the diagonal and 0 on the upper parts. And then now we have minus 3, 0, and 1, right? Because I said the L must have a negative going in, and then U again here, you see you have 0 on the diagonal, 0 here, and then now you have minus 3, 0, and 1. Okay. So then the next step is to compute your TG, right, which consists of D minus L inverse times U, and then your CG, which consists of D minus L inverse of B. Okay, and then once you do these two, then it is straightforward for you. It is straightforward for you to be able to now compute your results as you want. Okay, then the next one is the relaxation methods. So the relaxation methods really follow from the Gauss-Seidel approach. So of course, these methods that I'm now presenting, I'm presenting them in the matrix form. Okay, and if you follow this form, it's helpful in the end. So this is the Gauss-Seidel, and then the relaxation. I said it follows from Gauss-Seidel approach. So as well, the same way if you have your AX is equal to B, you can again if you follow the Gauss-Seidel approach, if you remember the Gauss-Seidel approach, what we had was we had X was equal to some D minus L inverse of U of X plus D minus L inverse of B. Okay, so it's really a relaxation of the Gauss-Seidel method, because you can see, for instance, if you look to the vector part here is the same as the Gauss-Seidel, but now with some relaxation parameters coming in, which is this W. And then if you look at the matrix part as well, you see that we have some D minus L inverse, and then this L now has some relaxation term here, and then we multiply it by we balance it with this 1 minus W of D plus W of D, and this gives us the relaxation method. Of course, for the relaxation method, if this parameter omega, which we call the relaxation parameter, right? So omega is the relaxation parameter. If this parameter is less between 0 to 1, then we call the method an under-relaxation method. And if it is greater than 1, then we call the method an over-relaxation method. So the name becomes successive, right? Successive over-relaxation method, right? Over-relaxation method, which is usually called the SOR. But the main question we want to ask is, how do you choose this omega? Is it random? How do you choose this omega? And there's a way, there's a technical way of choosing this omega, given by this formula here, right? Given by this formula here, where where you need idea of the eigenvalue, the maximum eigenvalue, right? Let me write this here. This is the maximum eigenvalue, right, of the matrix from Jacobi, right? The Jacobi, when we do the Jacobi method, that the TJ we have, you need that eigenvalue, the biggest eigenvalue, the maximum eigenvalue. So that's a nice way of choosing this omega, right? If you use this technique to choose the omega, the relaxation parameter, then you know that your method will go faster, or you get a faster convergence. Okay. Of course, then we did talk about, we did also talk then about some norms, okay, some norms, because we wanted to talk about stopping criteria. It's important that we talk about the norms. So what are these norms? So for norms, we define the norm as a function. So it's a function. This function here, it looks like this. It's like 2 bars from an Rn to R. that satisfies all properties, right? A vector, the norm of the vector should be greater than 0 for all x in Rn. For every vector you take, and then it should be equal to 0. The norm should be 0 if the vector is 0, and then the scalar, the norm of the scalar and the vector is equal to a scalar multiplying the norm of the vector, and then the norm of the sum of two vectors is less than the sum of the norm of two vectors. Right. Usually people call this a triangular inequality. A triangular inequality. The last one. Okay. The last one. Of course, so we want to talk mainly about two particular type of norms, the L2 norm and then the L2 norm. If you have a vector, that L2 norm is the sum of the squares of the elements of the norm, the square roots of the sum of the squares of the elements of the norm. Okay, so if you have example, if you have x is equal to 1 and 2, then if you want to take the L2 norm, it says that the square root of the sum of squares of the individual elements is like that, and this will give you square root of 5. Then there's the L infinity norm, right? L infinity norm. So this is the L2 norm. Then there's the L infinity norm. The L infinity norm is the maximum of the absolute value of the individual elements in the vector. Okay. So similarly, if you can have the distance between two norms, right? So this one particularly is on distance between norms, right? The distance between norms, between two vectors. So if you have one vector x, another vector y, and you want to find the difference between these vectors, then the difference is actually the square root of the sum of the differences, square of the differences. Okay. So it's exactly the same thing if you want to do the L infinity norm as well. So, of course, one important thing that we also want to talk about is stopping criterion, right? Stopping criterion is very, very critical when it comes to these methods. Stopping criterion. The stopping criterion. So, if you, for instance, if you have a matrix A, okay, consisting of maybe 4, 3, 0, 3, 4, minus 1, 0, minus 1, 4, right? And some B, which is equal to some 24, 30 minus 24. If you want to solve this using these methods that we've spoken about, the question is, when do we stop? Can we, because we are solving an xk to be equal to tx k minus 1 plus c, where we know k goes from 1, 2, and so on. When do we stop? It's really an important question of, and then this is what brings us to the stopping criteria. So if you are giving a system like A with B, then a good stopping criterion would be that if, for instance, example, if you compute, okay, up to x10, okay, if you stop at s10, then you can use a stopping criterion. So the stopping criterion means that you can take the relative error or the absolute error, whichever one. Usually the relative error is better. So if you want to do the relative error, for instance, then what you do is basically that you take your stopping iteration minus the iteration before, right? And then find and divide this over new iteration that you have. This is really important to determine the stopping, to help you in choose the right stopping criteria. Okay, so you take your x, so whether it's in L2, okay, or you want to do also for maybe L infinity example, is that you do the same x9 over x10, right? And if you do this, you get a value, and this you can use as your stopping criteria. That's when you do not know the exact value, right? You can use it as criteria. Of course, in some cases you know the exact value. If you know the exact value, for instance, and if you know the exact, right? If you know the exact, then all you have to do is, if you stop at 10, then you subtract from the exact, right? And then, so this is exactly the definition, and then you divide by the exact, right, in the same norm. Let me call this where this, right, where this is the exact one. Okay, so this is where I'll end, and hopefully with